Good evening, everyone. My name is Saransh and I'm a lecturer in Suresh Gyanvihar University. And today we will discuss about Planck constant, which is the part of this subject, heat and mass transfer. Here we will discuss about some content, like first of all introductions of Planck constant. Second is the laws. Third is the different form of waves, and the fourth is some multiple choice questions. First of all, we will discuss about the constant. Planck laws describes the spectral density of electromagnetic radiations emitted by a black body in thermal equilibrium at a given temperature T, when there is a no net flow of matter or energy between the body and its environment. At the end of the 19th century, physicists were unable to explain why we observed spectra of a black body radiation, which were then had been accurately measured, uh, diverged significantly at a higher frequencies from that predicted by existing theories. In 1900, Max Planck holistically derived a formula for the observed spectrum by assuming that a hypothetical electrically charged oscillator in a cavity that contained black body radiation could only change its energy in a minimal increment E that was proportional to the frequency of its associated electromagnetic wave. This resolved the problem of the ultraviolet catastrophe predicted by the classical physics. This discovery was a pioneering insight of the modern physics and is of fundamental importance of the quantum theory. Every physical body is potentially and continuously emits electromagnetic radiations and the spectral radiance of a body. P describes the spectral emissive power per unit area, per unit solid angle of the particular radiation frequencies. The relationship given by the Planck's radiation law given below show that with increasing temperature, the total radiated energy of a body increasing and the peak of the emitted spectrum shifts to the shorter wavelengths. According to this, the spectral radiance of a body for frequency V at an absolute temperature T is given by b, which is a function of v into t, is equal to 2 into h into v cube divided by c square into the 1 upon the uh, c ki power hr into the h into b ki power t minus the 1, where where kb is the Boltzmann constant, h is the Planck constant, and the c is the speed of light in the medium, whether material or vacuum. The spectral radiance can also be expressed per unit wavelength lambda instead of per unit frequency by choosing an appropriate system of unit of measure. Natural Planck units, the law can be simplified to become b, which is a function of v into t, is equal to 2 into v cube into 1 divided by e ki power w upon t minus k1, equating the integral of the spectral radiance in per unit area wavelength to that per unit frequency. Summation is a function of which is limit is lambda into lambda 2 b into the lambda b, which is the function of lambda and t d lambda, which is equal to integration b into v, which is the function of the lambda 1 and lambda 2 into the b into the v into t into the dv, is equal to summation integral lambda into summation limit is lambda 1 to lambda 2 into b, which is a function of v and t, where v is the velocity and t is the temperature, and the derivative is dv upon d lambda into the dx is equal to summation lambda 1 to lambda 2 minus the b into the v into t into dv upon d lambda into the d lambda, where the second integral integrates from v lambda to v lambda 1 because they're integrating forward in frequency space is integrating backwards in wavelength space. Wavelength increase as frequency decrease, so it lambda 1 is less than lambda 2, and then v, which is a function of lambda 2, is less than the v into lambda 1, because the equation holds to any limits. B, which is the function of lambda and t, is equal to minus the b, which is a function of v into t into dv upon d lambda. Using e is equal to lambda into v, we see that b, which is a function of lambda and t, is equal to minus k 2h square upon में lambda की power 5 into में 1 upon में e की power e upon में kb की power t minus k 1, showing how radiated energy emitted at shorter wavelength increase more rapidly with temperature than energy emitted at a lower wavelength. The law may be also be expressed other terms such as the number of photons emitted in a certain wavelength or in the energy density in a volume of a radiations. The SI units be V S to power minus k1 meter inverse into the hertz to power minus k1, while increase of B1 and V and W into the SR minus k1 and meter minus cube, showing how radiated energy emitted at a shorter wavelength increase more rapidly with temperature than energy emitted at a lower wavelength. The law may be also be expressed in other terms, such as the number of photons emitted at a certain wavelength, or the energy density in a volume of radiation. The SI unit of BV are watt into my SR inverse into my meter square into my hertz inverse, while those of B lambda are is equal to watt into my SR inverse into my uh, meter minus cube. In the limit of low frequency, long wavelengths, Planck's law tends to the relief genes law, while in the limit of high frequency, small wavelengths, it tends to the Wien approximations. Max Planck developed the law in the 1900 with only empirically determined constant, and later showed that the expressed as an energy distribution. It is a unique stable distribution for radiation in thermodynamic equilibrium. As an energy distribution, it is one of a family of thermal equilibrium distribution, which include the Bose-Einstein distribution and the Fermi Dirac distribution and the Maxwell-Boltzmann distribution. A black body radiation. And now we will discuss about the black body radiation. A black body is an uh, a black body is an idealized object which absorbs the emits all radiation frequency. Near thermodynamic equilibrium, the emitted radiation is closely described by Planck's law, and because of its dependence on temperature. Planck's radiation is said to be the thermal radiation, such that the higher the temperature of a body, the more radiation it emits at a every wavelength. Lung radiation is the greatest amount of radiation that any body that thermal equilibrium can emit from its surface. Whatever its chemical compositions or surface structure, the passage of radiation across an interface between media can be characterized by the emissivity of the interface. The ratio of the the ratio of the actual radiance to the theoretical Planck radiance, usually denoted by the symbol E. It is a general dependent on chemical compositions and physical structure, on temperature, on the wavelength, on the angle of passage, and on the polarizations. The emissivity of a natural interface is always between E is equal to 0 and 1. Different form of Planck's law. Planck law can be encountered in several forms depending on the convections and the preference of the different scientific fields. The various forms of the law of the spectral radiance are summarized in the table below. Form on the left are most often encountered in experimental fields, while those on the right are most often encountered in the theoretical fields. Corresponding between spectral variable forms, spectral energy density form, and the first and the second radiation constant. First of all, we will discuss about the correspondence between spectral variable forms. Here, we will discuss about the two topics, 2 points. First of all, is different spectral variables require different corresponding forms of expression of the law. In general, one may not convert between the various forms of Planck's law simply by substituting one variable for another, because this would not take into account that the different form have different units. Wavelength and frequency units are reciprocal. Corresponding forms of expressions are related because they express one and the same physical fact. For a particular physical spectral increment, a corresponding particular physical energy increment is radiated. This is so whatever it is expressed in terms of an increment of frequency dV or correspondingly of wavelength d lambda. Introductions of a minus sign can indicate that an increment of frequency corresponds with decrement of wavelength. In order to convert the corresponding forms so that they express the same quantity in the same unit, we multiply by the spectral increment. Then, for a particular spectral increment, the particular physical energy increment may be written. corresponding between spectral variable forms. Different spectral variables require different corresponding forms of expression of the law. In general, may not be converted between the various forms of Planck's law simply by the substituting one variable for another, because this would not take into the account that the different forms of the different units, wavelength and frequency units, are reciprocal. Corresponding forms of the expression are related because they express one and the same physical fact for a particular physical spectral increment. A corresponding particular physical energy increment is radiated. There is so whatever is expressed in terms of an increment of frequency dV or corresponding of wavelength d lambda. Introductions of minus sign can indicate an increment of the frequency corresponds with decrement of wavelength because frequency and wavelengths are inversely proportional to each other. When we increase the frequency, then decrease the wavelength, and we increase the wavelength, then decrease the frequency. In order to convert the corresponding forms that they can express the same quantity in the same units are multiplied by the spectral increment. Then, for a particular special spectral increment, in the particular physical energy increment may be written as b lambda, which is a function of lambda and t into d lambda is equal to minus k b into v minus k bv into, which is a function of v lambda and t into dv, which leads to b lambda into b lambda, which is a function of lambda and t, is equal to negative sign dv upon d lambda into my bv into my v into my lambda and t. Also, v lambda is equal to c upon lambda, so that the dv upon d lambda is equal to minus k c upon lambda square. Substitution gives the correspondence between the frequency and wavelength form with their different dimensions of units. Corresponding b lambda t upon bv is equal to c upon lambda square is equal to v square upon c. Eventually, the locations of the peak of the spectral distributions of Planck's law depends on the choice of the spatial variable. Nevertheless, in a manner of the spectrum, this formula across that the shaper of the spectral distribution independent of temperature according to Wien's displacement law as detected below in the subsections to Planck's of the sections. First and second radiation constant. In the above in in the above variants in the above variants of Planck's law, that wavelength of the whatever variants used in the form 2k square and the kc upon k lambda, which compute physical quantity uh, only only consequently, this term can be considered as a physical constants themselves and are therefore referred to as the first radiation constant Cu, and the second radiation constant C2 with C lambda is equal to 2hc into square and C2 is equal to Kc upon Kb. Using the radiation constant, the wavelength variant of the Planck's law can be written as L, which is a function of lambda and T, is equal to C1L upon by lambda power 5 into 1 upon by exponential EV upon by lambda 1 F minus K1, and the wavelength variant can be simplified correspondingly. L used is the instead of B because it is the SI symbol of the spectral radiance. The LCl refers to that the reference of a necessary because Planck's law uh, can be referenced to the gave spatial radiant uh, extents rather than the spectral radiance, which is the C1 replace C2. C1 is equal to 2 pi square C square, so that the Planck's law on the spatial radiant existence can be written as the M, which is a function of lambda and T, is equal to C1 upon lambda ki power 5 into my 1 upon my exponentially C1 upon my C2 minus K1. Now we will discuss about some multiple choice questions. The first question is the energy emitted by a black surface should not vary in accordance with option A wavelength, option B temperature, option C surface characteristics, and option D is time. So the correct answer is option D time. It is a time independent. For a prescribed wavelength, the body radiates much more energy at elevated temperature. Likewise, the amount of emitted radiation is strongly influenced by the wavelength, even if the Temperature of the body is option A constant, option B increasing, option C decreasing, option D it is not related with temperature. So the correct answer is option A constant because the temperature must remain constant in order to emit radiation. Question number 4. A small body has a total emissive power of 4.5 kilowatt per meter square. Determine the values of emission maximum. Option A 8.46 micron, option C 7.46 micron, option C 6.46 micron, and the option D is 5.46 micron. So the correct answer is option D 5.46 micron because the wavelength maximum T is equal to 2.89 into 10 power minus 3. The sun emits maximum radiations of 0.52 micron meter, assuming the sun to be a black body. Calculate the emissive ability of the sun's surface at the temperature. Option A 3.47 into 10 power 7 watt per meter square. Option B 4.47 into 10 power 7 watt per meter square. Option C 5.47 into 10 power 7 watt per meter square, and option D is 6.47 into 10 power 7 watt per meter square. So the correct answer is option C 5.47 into 10 power 7 watt per meter square because the formula of this radiations for the micrometer in a black body radiation is denoted by capital E is equal to summation B into the T power 4. Uh, putting the value in this formula, then we get 5.47 into 10 power 7 watt per meter square. So the correct answer is option C 5.47 into 10 power 7 watt per meter square. Next, the law governing the distribution of the radiant energy over a wavelength for a black body at fixed temperature is referred to as option A Kirchhoff's law, option B Planck's law, option C Wien's law, option D is Lambert law. So the correct answer is option B Planck's law. Question number 7. The Planck's constant H has two dimensions equal to option A ml square t inverse, option B ml t inverse, option C ml t की power minus 2, option D is m into L into t. So the correct answer is option A ml square into t inverse. It has a unit equal to joule second, and it is the value of 6.262 into 10 to the power minus 34. Question number 8. Planck's law is given by option A. EB is equal to 2 pi c square into h into wavelength power minus 5 divided by ch divided by k wavelength t minus 2. Option B. EB is equal to pi c square h into my exponential ch upon k wavelength t minus 10. Option C. EB is equal to 2 pi c square h into wavelength की power minus 5 divided by exponential ch upon k wavelength t की power minus 1. And option number D, EB is equal to 2c square into h into wavelength की power minus 5 divided by exponential into by ch upon k wavelength t की power minus 6. So the correct answer is option C. Option C, EB is equal to 2 pi 2 pi c square into h into wavelength की power minus 5 divided by exponential ch upon k wavelength t minus k 1, because Planck suggested the following law for the spectral distribution of a emissive power. A furnace radiation at a 2000 Kelvin, treating it as an black body radiations. Calculate monochromatic radiant flux density at 1 micron meter wavelength. Option F 5.81 into 10 to the power 7 watt per meter square. Option B 4.81 into 10 to the power 7 watt per meter square. Option C 3.81 into 10 to the power 7 watt per meter square. Option D is 2.81 into 10 to the power 7 watt per meter square. So the correct answer is option D 2.81 into 10 to the power 7 watt per meter square, because EB is equal to C1 into wavelength की power minus 5 divided by exponential into C2 upon wavelength t की power minus k1. When we putting the formula in this putting the value in this formula for a black body radiation for a monochromatic radiation flux, then we get option then we get result is 2.81 into 10 to the power 7 watt per meter square. So the correct answer is option D 2.81 into 10 to the power 7 watt per meter square. Next, a metal is a metal sphere of a surface area 0.0225 meter square is an evacuated enclosure whose walls are held at a very low temperature. Electric current is passed through resistors embedded in the sphere, causing electrical energy to be dissipated at a rate of the 75 watt. If the sphere surface temperature is measured to be 560 Kelvin, while in steady state calculate emissivity of the sphere surface. Option A 0.498, option B 0.598, option C 0.698, your option D is 0.798. So the correct answer is option B 0.598 because the formula of this situation is equal to for a sphere space in a black body radiation for electric current. So which is denoted by capital E is equal to small e into the A into the summation into the small b into the capital T, and the put the value in this formula. Then we get the result is option 0.598. So the correct answer is option B 0.598. Last but not least questions. The Stephen Boltzmann constant has unit of option A kilokelvin per meter square, meter square into har into the kick power minus 4. Option B kilokelvin per meter har kick power minus 4. Option C kilokelvin per har kick power 4. या option D is kilokelvin per meter square kick power 4. So the correct answer is option A kilokelvin per meter square into har ki power into k ki power 4. uh, Explanation is according to Stephen Boltzmann law, Q is equal to alpha into A into T to the power 4. Thank you.